All right. The second kind of bond that we're going to talk about are ionic bonds. So sometimes an atom will pull so hard on another atom's electron that it'll entirely just strip the electron away. When this happens, now you're transferring a negative charge from one atom to another atom. And so this results in the two atoms now developing opposite charges, right? So the atom that gained the electron gains an extra negative charge and becomes negatively charged. And the other atom that lost the electron now lost a negative charge, so it has one extra proton, and it will have, therefore, a positive charge. And what we know about opposite charges, when you have positive and negative, they're going to attract to each other. And so when these atoms transfer an electron from one to the other and they develop opposite charges, they start to stick together. And that attraction between an oppositely and positively charged atom is going to result in an ionic bond. So a couple of new terms perhaps on this slide. When you have a charged atom or molecule, it's going to be called an ion. And we have two different kinds of ions. You can either be positively charged or negatively charged. So cations are going to be positively charged ions. If you like cats, that's a positive thing. Think cation, positively charged. If you don't like cats, you got to think of something else. And then anions are going to be the negatively charged ions. Anion looks a lot like onion. Onions make you cry. That's negative. So maybe that'll help you remember cation versus anion. But regardless, when you have this transfer of an electron, it creates a cation and an anion. The two are going to want to stick together. And that attraction between the negatively and positively charged particles is the ionic bond. Make sure you understand that it's not the transfer of the electron that's the ionic bond. It's what happens after the electron is transferred. When you have the creation of those two oppositely charged particles, an opposite charge is going to attract. And that attraction between those two oppositely charged particles is the ionic bond. All right, an example. We've looked at this example briefly in an earlier video. This is the formation of table salt, right? So we're looking at a sodium atom. It's got that one valence electron. And we're looking at a chlorine atom. It's missing one more valence electron, so these two make a really good pair. Sodium says, hey, chlorine, I will give you my one valence electron. And when it does so, it has no more electrons in the third shell. Third shell doesn't exist. And so we form a sodium ion. This is the cation. It lost an electron, so it's an extra proton, one positive charge, and that third energy shell has disappeared. And so now the valence shell is the second shell. That one's full. Sodium's good. Chlorine is also going to be good. It gains that one electron, gains a negative charge, becomes the anion with that one extra negative charge. And now it went from 7 valence electrons to 8 valence electrons. Its outermost shell, that third energy shell, is going to have those 8 electrons it was looking for per the octet rule, and it's happy as well. And you've got a positive charge, negative charge. Those two ions are going to want to stick together, and that's the formation of an ionic bond. Now, ionic bonds typically are going to form ionic compounds or salts. So salts like sodium chloride, table salt, are often found in nature as crystals. And so here you can see the nice lattice work of the sodium and chloride ions within that salt crystal. It's a 1-to-1 ratio in this case. So you can have lots of different kinds of compounds. You have compounds that are molecules. You can also have ionic compounds. This is the case where you have those atoms being held together not by covalent bonds, because that would be a molecule. But if it's an ionic bond holding together those atoms, that'll form an ionic compound. All right, now this might be a good time to talk about strong versus weak bonds. We've talked about so far ionic bonds and covalent bonds. Most of the strongest bonds in organisms are going to be covalent bonds that form the cell's molecules. That's really the basic building block of a cell, right? These molecules that are going to come together to form the structure of the cell. Weak bonds in biology are also indispensable, though, and these are going to include ionic bonds, which we already talked about, hydrogen bonds, which we will talk about, as well as van der Waals interactions. Now, if you've taken chemistry, I hope you're thinking, hold the phone. My chemistry instructor told me that ionic bonds are some of the strongest bonds out there. Yes, I will not disagree, right? So going back to the salt crystal, right? If I had a nice chunk of salt, I put it on a table, how difficult would it be for me to break it apart? I probably couldn't do it just by hand, right? I would need a hammer or a chisel or an ice pick or something. That's an indication that those ions are held together really well, right? So yes, ionic bonds are really strong. However, living organisms depend on water, right? We are 70 to 90% water ourselves. We live on a planet that's 3/4 covered with water. And so in living organisms that are dependent upon water and are made out of such a large amount of water, things change a little bit, right? If I take this big chunk of salt now and put it in a kiddie pool size body of water, what's going to happen to that salt? It's going to dissolve, right? It's going to completely break apart. I don't need a hammer or an ice pick or a chisel to get that to happen. It'll just fall apart completely on its own. So in living organisms that are dependent upon water, based on water, ionic bonds are going to be much weaker than covalent bonds. Okay, and then also hydrogen bonds and van der Waals interactions. We're going to tackle these next. They're also weak. Now, weak has a negative connotation, but keep in mind that weak bonds are probably just as important as strong bonds in biology. Many large molecules, their atoms might be held together using covalent bonds, but the actual three-dimensional shape of that molecule is also really important. We're going to talk about how form equals function. When a molecule doesn't have the right shape, it's not going to be able to do the right job. And so this three-dimensional shape of these molecules is oftentimes held together with like little, you can think of paper clips and tape and staples here and there. Those weaker bonds, like hydrogen bonds, van der Waals interactions, ionic bonds, help to hold these three-dimensional shapes for these molecules to help them function. So that's very important. Also, weak bonds are reversible. And this is important in biology. You don't always want two things to come together and stick permanently. You want sometimes this transient, come together, fall apart, come together, fall apart, to happen between molecules and living organisms. Let me give you an example of where these weak bonds would be important. So I'm going to draw a cell. There's my cell, got a nice little nucleus. And let's say this cell is a cell that can and so it's got a little receptor, a little protein on the outside here that's like a little mailbox for the insulin hormone. And so when your body produces insulin, I'm going to draw insulin as a little triangle, insulin can come along and it can bind to the receptor here on the surface of the cell. And when this binding occurs between the insulin and the receptor, it tells the inside of the cell, hey, you need to start pulling blood glucose out of the blood so that we can maintain normal levels. You don't want the insulin to attach to the receptor and stay there, right? Because if you take out too much blood glucose, that's bad too, right? You need to make sure that you've got this nice balance, having the right amount of blood glucose. So as soon as you reach that good blood glucose level, you want that little insulin molecule to go away so that you no longer give the cell the signal to take up that blood glucose. Right, so this interaction between the insulin and the receptor is mediated by these weak bonds or weak interactions that can allow molecules to interact, but also allow them to detach.